So I will give you an introduction to the numerical software and also give you logistics and some other additional things. So let's just make sure first I have a laser pointer. Okay. So here, I will first say a little bit about the logistics for the day, and then I will talk more general about algorithms, CSE, et cetera, et cetera. So first of all, you probably all know this already, where you can get your home bases here, your agenda. You can find them on the ATPESC website as well. We do have our math packages training sites. I don't know if you've looked at this before. It's over here, actually. And so you can get to the agenda there as well. So here you can see when you go to this math packages training site, then you can see that there are several of these parts here where you can click on, and when you look at the intro, click on the intro, you can see there are a set of instructions. That's for our hands-on exercises, which we'll have for each of the different lessons we have later for the individual algorithms and codes. There's today's agenda. Then you can see the VIP talks. I'll say a little bit more about that later. Then if you need help, there's also a tab for that. You can click on that, tell you how to get help. Then there's a session selection survey. I'll say a little bit more about what that means in a little bit. Then there's a panel question submission. We do have a panel today, and you can submit questions there. And then also there is a speed dating where you'll have a chance later tonight to talk to one of our experts here and sign up for that. So here's our overall agenda. You can see here there are different all the different lectures we provide today. And one thing you might notice here, I have these room question mark things. As you know, we have 2 rooms. Since we didn't really know, and the second room is actually smaller than this one, we didn't know how many people would sign up for which sessions, since there are 2 types. We actually provide you guys the opportunity to sign up so we can make an estimate, and we might switch the rooms. There might not be like what's in the program. So in order for you to make the decision, I will tell you a little bit about each of the different packages beforehand so you can decide which ones is more of interest to you. So let's get started. Oh yeah, and let me first say what you have to do. I told you before, when you go to this math packages training website, you click on the selection survey here where you can select which lesson to attend, and this will give you this form, and there you can make your selection. So you can either say one, structured or unstructured, or you can say you really don't know, in which case you might end up having to go in the bigger room. Okay, so let me say a first thing. So the first part at 9:30, we actually have 2 different packages or 2 different discretizations to talk about. On the one hand, a structured discretization, and on the other side, unstructured discretization. So let me say a few things about the codes. So the structured discretization is done by the AMREX package, which has a lot of different capabilities. It allows you to support PDEs on hierarchical adaptive meshes. And for example, different applications that need this is accelerated modeling, astrophysics, combustion, etc. So that's one option. The other option is if you do want to have more different types of more complex structures in a way, but that can't be that easily well-performed. Structured meshes you can get better performance out of it. But if you have unstructured ones, there are 2 different packages we are actually introducing here. MFEM, which is a finite element package, you can see here, which gives you a variety of different ways to get unstructured grids, including even high-order finite elements. And then there is PUMI, which is another parallel unstructured mesh package. So again, so you can make a decision between structured and unstructured. Then after the break, we do provide 2 options. You can either do iterative solvers, which includes and preconditionals, which the main one is algebraic multigrid here, or direct solvers. So you can make a decision between that. I should say, if you really like direct solvers, but you also want to learn about iterative solvers, you will have another chance to do this later with a different package. So let me say a little bit about the 2 packages actually 4 packages that will be introduced for these. On the iterative solver side, Trilinus is actually a big package which has a variety of different software packages underneath, a collection of different packages. And so one of them, which is considered here as Belos, which has Krylov solvers. And then the other one is Mulu, which is the Trilinus algebraic multigrid solver. So you can learn more about those, and you can have some hands-on exercises using those. On the direct solver side, you have SuperLU, which is a sparse LU direct solver. Keep in mind, and generally you can, if you really have large systems, iterative solvers generally perform better, but you might have problems which are harder to solve, in which case direct solvers are the ones you might have to go to. And so SuperLU is a sparse LU direct solver. And then there's also StrumPack, which is a dense matrix solver but uses hierarchical approximations and also has a sparse direct solver underneath. So if you want to do that, you can choose between those two. Then after lunch, we do have 2 sessions. On the one hand, they're nonlinear solvers, and then time integration on the other side. So let me first talk about sundials. That's the code where you can learn about time integration. Sundials also provides nonlinear solvers, but here the focus will be on the time integrators. So you can learn about these here again. And on the other side is ATPESC that provides also time integrators, as you see, as well as nonlinear solvers, but the focus for this section will be the nonlinear solvers. It also has Krylov solvers, preconditioners, etc., but as I said. And it also has tau, which is the optimization component, and which will be talked about afterwards. So again, those are the packages here. So at 3:15, you will have the optimization will be discussed there, and opposite of this is your second chance of doing iterative solvers if you didn't do it the first time. And in this case, you get iterative solvers and algebraic multicode using Hyper. That's a different package. So Hyper here, that's one of the packages I work on, so I really like it. But Mueller is great too, so I just want to say that either way. I don't know. So Hyper actually does also have different interfaces. So part of this will also look at structured versus unstructured a little bit. And again, all these packages do have some GPU implementations, I should say. So you'll hear about GPUs a little bit too, because I know that's really what people are interested in nowadays, so, especially with regard to exascale. Okay, so this was essentially what I wanted to tell you about. You can start making your selection now, or you can wait a little bit because you'll learn a little bit more about this as I go ahead. But I really ask you guys to have this done before the end of this presentation, because we already will immediately, after this, Anne and Eric will start talking about, we will have both structured and unstructured discretization. So, okay, so let's go back to a math packages training side. You can also, the hands-on exercises are found under this lessons tab here. And then you can also have these packages slides you can look at again under the packages tab. So, okay. So, and then I do want to say a little bit more. Today at 4:30, we actually have this combined wrap-up panel session. I know by that time you're probably all slain and tired and so on, and almost ready to go to. So that's why we try to make it a little easier. So the wrap-up first will be done by Anne Argonne. It's like a 15-minute easygoing talk, and then there will be the panel afterwards. By that time, I should say you need to also provide the panel question if you have any by 3:15, so before then. And already before the optimization iterative solver session. And then by 6:30, by that time, you really need to sign up for the SME, the opportunity to talk with one of the experts, one of the software developers. You can talk with several, of course, again. Okay, and just one more thing about the panel. So the panelists are going to be these 5 wonderful people here, and Richard Mills is going to be moderating that. The topic will be extreme scale numerical algorithms in software. So if you have questions, please submit those. So, okay, and then of course we're using Slack. I'm assuming you've been doing this all along. So if you need help, take advantage of Slack to ask questions there. In the worst case, you could also try to email to some people directly if you go to our tab. But I think you are by now all versed in doing this. So let me now get to the actual track we have here, numerical algorithm software. So why are we even doing this whole section? So we wanted to make sure that you all get a basic understanding of a variety of different applied math algorithms that are very important within Extreme for a lot of different simulations. So you will be allowed to learn about scalable linear, nonlinear solvers, all kinds of discretization techniques, etc., as well as optimization. So, and then we do want to give you an overview of the software tools that are available for you that you can use, and also provide you to allow you to use them in our hands-on exercises. So it does also give you a high-level introduction to the HPC numerical software, so what's available there, how important it is actually for CSE, for computer science and engineering, And that part of, I will say a little bit more also about extreme scale ecosystems we have in order to really run big simulations on our new exascale computers requires a lot of different software. And then also you get some more information how you can actually help out with that, how you can learn more, even for your own software implementations. Although I believe you're learning a lot outside of this in the other tracks as well. So why are libraries actually important for you? Because it helps you to take advantage of the expertise of other people. They have figured out how to implement them in a good, high-performing way on different architectures. They have learned the algorithms and figured this out. So if you can take advantage of this, you don't have to learn this, and you can just use it for your science application. And hopefully, this also will help you to get overall much better software. If you're writing your application code, for example, you take advantage of that. And that ultimately, we hope that we can get better science as a consequence of this. So here's our current team for this track. You have all of us here that are involved in that today. So I'm not going to go into that in detail. We don't have time. But I do want to point out the VIPs. So in the past, we always had speakers here. This time, I just noticed yesterday, we had one. But Jack Dongara is going to be, his talk will be tomorrow evening. So I want to point this out. Make sure you go there. He's actually one of the people out there who really knows a lot, a really well-known expert. But there are also the other previous Jim Demmel and David Keyes are also some very great experts. We have provided slides and videos for them for past talks they've given. So go check them out as well. OK, so now let's get started and talk about how did we even come up with all these different software libraries we have. It actually really involves decades of work that has been done over a long period, more than 20 years, et cetera. And so there are various different institutions that have been very helpful towards that. Most recently was the Exascale Computing Project, which of course is a very big project across DOE, which involves DOE's Office of Science as well as the National Nuclear Security Administration. And that's one of them. Then there's the FastMath SciTech Institute, which we already at number 5, so it's been around for many, many years as well. And then, of course, the developers of XSDK packages. I'll tell you more what XSDK is later. And then, of course, we do have some areas like there's the IDEA Software Productivity Project, as well as the Better Scientific Software Community, where you can get information on how to actually write better software yourself and so help you overall to do better with regard to that. So let me first say a few things about FastMath. So the overall goal for FastMath was really to allow to advance numerical methods for the different DOE applications on the Office of Science side and make sure that they work well on high-performance computers. So that's what's been happening there for many, many years. The current FastMath 5 Institute actually has 8 different areas. 5 of them are actually covered today in a way, like structured and unstructured discretization, time integration, and linear and nonlinear solvers, as well as optimization. And so you see there are lots of researchers from 5 different labs, 5 universities involved, and it has a lot of different math software. This is not even all of it, but it's just give you an example. Now, the ECP, it's a little newer project than FastMath Institute, and the basic idea for ECP was to enable exascale computing. So it started in, 2017 or whatever, but I mean, it's going towards an end, so it should only be going for another 1.5 years maybe. But the basic idea was to try to get a lot of different experts from various different areas. You can see from the application side, software technology, and hardware and integration together to make sure we actually get our goal, achieve exascale. And so, of course, the focus for us here is math libraries, which are part of the software technology section in the ECP. So then let's talk about CSAD. So what is computational science engineering? It's essentially a conglomeration of 3 different disciplines: mathematics and statistics, computer science, and science and engineering. And all these we're trying to work together to advance simulations, to make more progress, to get all branches of the sciences together and make some really good progress with this. There's actually a report here, if you're interested to learn a bit more here, that was written in 2018. You can learn a little bit more about the role of CSE and their directions toward predictive science. So there's a link to it. And one of the important parts of CSE is, of course, software. So you can see here's a nice little diagram which shows you important areas for CSC, which has models as well as data, et cetera. But without the software, you can't really do much, right? So it is very important. So it is important that we do provide good software that helps us to move this forward. So what's a typical CSIA simulation? So how does it actually start? How does this work together? So you have CSE. So you first try to develop a mathematical model of interest, like you have a certain physical or whatever phenomena, and you want to know how can I learn more about it? How can I simulate this in a way? So you first come up with a mathematical model, then you approximate it using some kind of discrete representation. You know, that's where our structured and unstructured discretizations come in place. You solve it, and then you probably want to adapt and refine, and you might want to add more additional physics. You might want to get more out of this, right? And so that's the basic loop that you have. Models, master discretization, and do the refinement. And of course, that involves a lot of difficulties. So the important part is really the CSE simulation loop, but of course there are other things that are very important. You know, you want to make sure that this all, what you get actually makes sense, and that's why there are things like uncertainty quantification. You want to analyze the data, you want to optimize the whole thing, and you want to go further. And so this requires a lot of different things, like data analytics, uncertainty quantification, differentiation, inverse problems, et cetera, et cetera. So this is a very highly complex point. But I do want to give you a small, very simple example on how to go about this. So assume we have a very simple example here. We do have the heat equation. So we have a 1D rod with one end in the hot water, the other in the cold water. And so you can make a very simple, easy mathematical model. You have your boundary conditions, 180 degrees of Celsius on the hot water side and 0 on the other side. And so you use this, and you use some kind of discretization method. The easiest one in this case is finite differences. You could use something like finite elements and finite volume, but that's really not required here, and it's kind of actually the same here. And so you determine this. You have your individual points. And once you have that equation, you can actually set up a linear system with this for all your different instances here on your rod, and include your boundary. And then you can actually compute this, you visualize this, and analyze the results. So, so you can kind of see how this gradually, over time, dissipates. Of course, this was a super simple problem. Generally, they want to solve a much more complicated problem. And so you can realize once you start having more difficult systems, more difficult grids, things get harder to do. So you might have, because you have some areas that need to be further refined, so you need something like adaptive mesh refinement. So you need special grids like this, or you need unstructured grids to do this. And you can see you also want to have more flexibility. So one thing that happens a lot of times, if you have a structured grid, you can get higher efficiency on a computer, but you have less flexibility for the type of problems you can solve. So you have to figure out which kind of sacrifices you want to. Then keep in mind, most problems are time dependent and they're nonlinear. So that makes it even harder to do. So they need to be more than linear solvers. You need nonlinear solvers. You need to have different ways of different time discretization methods of different orders, et cetera. And then, because we do want a multiphysics problem, we want to combine multiple physical processes. So you have to be very careful when you put them together to make sure what you get in the end still makes sense. And so that's why you do need optimization. You need uncertainty quantification, sort of looking at your results later and say, does this even really make sense? Is this even what I want to see? So let's take a look at what different types of things you have. So on the structured side, you might have you want to do some block structured adaptive mesh refinement. And you can focus on higher order grids, mapped grids, in order to get better resolutions, et cetera. And there are a variety of different applications that need that, where you can actually use structured grids. For example, cosmology, astrophysics, accelerator modeling, fusion, combustion, subsurface reacting flows. For all these ones, you can actually use structured grids. And because you can use structured grids, you can get some very efficient implementations. But again, so it is important that you can do AMR. However, you might have some more out of the ordinary or different grids that are more complex, where you actually need some different ways of discretizing then, and so you can have some finite element discretizations and use some unstructured grid capabilities. And again, none of this is really easy, because you also have to keep in mind when you actually try to put these grids together, put them on a parallel computer, it involves a lot of different load balancing. You have to make sure that you're using the same amount on each process, et cetera, et cetera. You need to make sure your meshes are still of good control, and so on. So we do have, like on the earlier for the structured part, we actually have AMREX. Here on the unstructured side, we have MFEM and PUMI today. So you can learn more about this if you want to learn about it. And in order to get good performance, again, this takes some a lot of examination of the architectures, et cetera. Now, in order, if you do have a time-dependent problem, you need to have some time discretization methods. You have to discretize across time. And there, again, there are a variety of different methods available, different implicit or explicit methods, multi-rate methods, the spectral deferred correction methods, and so on. There can also be parallel time methods, et cetera. We're not really going to talk about them here. Applications for those are in atmospheric dynamics, ice sheets, power grid simulation, et cetera. And so one of the packages that provides these is sundials here, and I guess so. And then, of course, when you do have your systems, they grow, and so you need to work with the corresponding discrete systems, and they can get really large. You have billions grid points and unknowns, and there are a lot of times they're sparse, so you deal with additional complications. So you can have direct methods, the Gaussian elimination, which we know can fill up. So again, this has to be handled carefully. In order to get really good performance on very large problems, you probably want to use some iterative methods where you can stay with your sparse systems, use them as preconditioners. And then there are other ways to get scalability. Again, some of this will be addressed in our solver sections today when we talk about iterative versus direct solvers, as well as preconditioners, et cetera. And so there are a variety of different software tools that help you to get this functionality, including ATPESC, SuperLU, Trilinos, et cetera. So you can learn about this today. And then, of course, you do want to not only linear systems need to be solved, but also nonlinear systems. Again, so we will talk about this today. Through PETSC provides nonlinear solvers. I guess Sundials has some as well. Then there are eigensolvers, and of course, we always try to do architecture-aware implementations. So you allow you to run on different types of different machines and do get good performance out of all of them. So. And of course, one of the primary motivator for exascale has been multiphysics. I already mentioned earlier, you might have different physics. You want to put them together for the really large simulations. And that's where it really becomes important that we do provide libraries, mathematical algorithms, because none of these physicists, et cetera, scientists out there can do everything. It really requires a lot of people to get a high, well-performing simulation on an exascale computer. And of course, we do need the software. So here's the DOE roadmap to exascale systems. As you can see, we are right now in this area. We do have Frontier. It came out as the first exascale computer in the US. And maybe, I mean, at least the first one that's recorded. There might be some others, we don't know. And of course, Aurora should be coming out soon, later this year. Or at the beginning of next year. And then next year we will have El Capitan. One of the things you might notice with all these new machines here is they all use GPUs, not Crossroads, but these here. But they all use different types of GPUs. I mean, we already had some of them here earlier. Summit, Sierra had already NVIDIA GPUs. And then, of course, we have Theta GPU, and I know today you get to do some hands-on using Theta GPU, which also actually has NVIDIA GPU. Even so, originally it was set up with KNLs, but there have been GPUs added. So you get to play a bit today with one GPU at least. And, but Frontier has AMD GPUs and Aurora Intel GPUs, and all of these use different programming models. So again, that's a challenge for the math libraries. And of course, it also causes, you get a lot of different changes because of these new architectures. You end up with different memory hierarchies. You have very high node counts, so you will have to have a lot of parallelism. You need to reduce communication. The individual cores are much faster. GPUs are super fast, but then you have communication overhead gets more crucial. So there are a lot of things we do have to deal with, especially when we're dealing with sparse systems. So again, there are a lot of challenges because of these new architectures. So it is important that we provide software libraries. And again, of course, the key advantage of a software library is that it gives you the complexity, contains the complexity for you, complexity for the developers. We still have to implement it. And you can actually leverage our expertise there. And it should help your application because you can just use them. So it's really important that these are provided. So there is a lot of different HPC numerical software out there. I have put little stars next to the ones that we're going to present today, so you can learn more about it today. But there are others, and this is just a small subset. There are a lot more. So. Again, one of the issues is when you have these math libraries, a lot of the applications out there need to use more than one. As a matter of fact, they use many in combination together. So here are a few examples of the application teams in the ECP. They do use, like, here's some examples. They use 6, 7, 8 or more math libraries in combination. So it's really important that these math libraries can be built together. If you ever build a big application software package, you know how hard it is. And a lot of them use 30 libraries or more, right? Not all math. There are other libraries involved. So that can be very challenging. And so it's really important that we work together among the math libraries to make sure that you can build them together if you want to use several of them. And so what's important is that you get some consistency when we use a compiler, that there are no conflicts in our namespace or version conflicts. You can have one package calling one version of a package and another one a different one, and you already start with some issues. We also need to make sure those packages, some of them interoperate with each other, that there's no conflicts there. So that's kind of very tricky. It is really important that we look how we're going to do this. And so here's this famous quote by Sir Arthur Stanley Addington that he says that a lot of times, even so we might know what 1 and 1 is 2, but we haven't really discussed what does and really mean. What does it really mean to put these things together? Especially since we're talking about a group of independent but interrelated elements that make a whole. Right? And in our case, we have independent libraries that have completely different strategy of implementing and so on and so forth. And how can we make sure that they don't impact each other in a negative way? And so for this one, we actually put together the XSDK, which stands for Extreme Scale Scientific Software Development Kit, right? So there's also, we have a website for this. And the overall goal here was just to make sure that they will actually work well together, that we do have good quality libraries, that they're sustainable over a long time, and so on and so forth. So here, this was our latest release in November. At this point, we have actually 24 math libraries. We do have 2 domain components also. And you can see, like, you might have a big application which uses some other applications underneath, and they in turn call our libraries. So when you want to build the whole thing together, you need to make sure that works well together. And as our builder, we use SPAC to build these libraries. Here's just, this requires still a lot of work. So we have a lot of people working together. This is not all of them. Here's just a few of the main people or the package POCs in a while. But there are a lot more people that I can't even list here that work on this, right? So we do use SPAC to deploy the software. And here you can see a tree, which was of our most recent one. The green ones are the XSDK libraries. But you see even underneath, they call a lot of different additional libraries. And all this has to work together. So. And again, here's, I just put up the logos of our current XSDK libraries. You can see they're all very diverse. Give you some idea how diverse actually the different libraries are. So again, so what did we do to make sure that they actually can work together? So the main idea is we came up with some guidelines that all of these libraries follow together. And so you can actually we call them the XSDK community policies. They are available on our webpage, but you can also get them on GitHub. where you also can provide input if you want to. And there are basically right now 16 mandatory policies that every package has to fulfill. They kind of address all kinds of things like installing, configuring. They all need to be open source, etc. Make sure there are no namespace conflicts, etc. And then the second condition to be an XSDK member package is that they need to interoperate with another XSDK member package. So, yeah. So again, if you have any feedback for that, we do regularly revisit the policies to see if we should make updates. So here's just, I'm not going to get into this, so don't worry. This is just a short form of all of them. We do also have some recommended ones, which many of the packages actually compatible with, but they're not required to do this at this point yet, at least. And so, for example, one could be provide a comprehensive test suite that really helps to improve code quality if they haven't done this before. Of course, all our packages do, and by now everybody, pretty much most software, every software developer out there knows that you need to do a lot of testing to make sure this keeps working. Another one we do have is give best effort at portability to key architectures. Now, again, what's that supposed to mean? It's very vague, and we purposely kept it this vague. But for all the software that is supported by ECP, this requires that these packages need to run on the upcoming exascale computers. And that's a challenge. I should say not all XSDK libraries are supported by ECP. So, we can't be quite as tough on everybody. So, again. And so it's important that they're port, but not only port, they also need to provide good performance, right? So there comes the word performance portability. So we want them to be performance portable. So what is performance portability actually? So I was starting to think about this, and I started to look on the internet a bit. And actually, I was trying to find a clear definition. And what I found was that there was actually a meeting on that in 2016 in Phoenix, Arizona, and which included a lot of different, it was a DOE meeting, different people, scientists, engineers, vendors, etc. All of these got together, discussed performance portability. What does it actually mean, right? And so here are some of the quotes, which I found interesting. They said, for the purpose of this meeting, it's the ability to run an application with acceptable performance across kernel, GPU-based systems with a single version of source code. Okay, so you just throw the code on. And then here, a little bit more complicated one. An application is performance portable if it achieves a consistent level of performance, for example, defined by execution time or a figure of merit or something like that, relative to the best known implementation on each platform. Now we're getting more complicated, right? Then there were some people talking about different types of portability. Hard portability, we don't change the code at all. Software portability, we just make some small changes. Or non-portable, if we have to make algorithmic changes, the code is not portable. Okay, that's one way. And then somebody said performance portability means the same source code will run productively on a variety of different architectures. And then finally, my favorite one, code is performance portable when the application team says it's performance portable. Okay, cool, I like that one. Okay, so you can already see there wasn't really a universally accepted definition of performance portability. Nevertheless, that team made an attempt to put one together. You can tell me if you like it or not. I don't really like it. But anyway, an application is performance portable if it achieves a consistent ratio of the actual time to solution to either the best known or the theoretical best time to solution on each platform with minimal platform-specific code required. I feel like this is too complicated and still kind of vague in a way. So I found a more reasonable one actually on the Best Scientific Software website by Anshu Dubey, which this is something I can work with. An application has portable performance if in addition to running on diverse platforms, it exhibits similar accuracy, stability, and reliability across these platforms for given configurations. Moreover, the time to solution should reflect efficient utilization of available computational resources on each platform. Okay, I like this one. I feel like this is more useful. So all these codes we're going to hear about later today are trying to make efforts towards that. But I wanted to give you some more ideas on what type of efforts they actually make for this. So for once, one thing they do is, of course, they try to use portable programming models that provide abstractions. For example, Cocos, Raja. I think you heard about some of them already during here. And then, of course, there's these newer one programming models, SYCL and Heap, SYCL by Intel and HIP by AMD. We promise that this will also work in the future. I hope it will, because some of us putting a lot of effort to put them into our codes. And then, of course, there's the use of abstraction to limit code that interacts with devices. So some of us have only very small parts in our code where we can add new programming models, and that's very helpful, so you can faster get onto a new machine. So another one, of course, is you do want to take advantage of fast kernels, libraries that are designed by the individual architectures, by the individual vendors provided. For example, on NVIDIA GPUs, cuBLAS, cuSparse are some of those. Then AMD has RockBLAS, RockSparse, et cetera. And then for Intel GPUs, that's MKL. So we're trying to take advantage of these as much as we can, at least where they're really working better in some cases. Another thing that some of us have done, because NVIDIA was there first, so they write CUDA corners, and then vendors actually do provide tools to try to port them over, like Hipify them if you want to go to HIP. Also, Intel provides some tools to port your kernels to SYCL. Again, this requires more work. It's never that simple, but it does help, actually. It has helped us in some of the cases to actually do that. And then finally, which is, for me, from the mathematical point of view, the most fun part, but also the most challenging part, and doesn't necessarily the fastest one, is to develop new algorithms that are more suitable for GPUs. We actually were able, for some of the libraries, to do this, and that was a lot of fun. So anyway. OK, so the XSDK is really the primary delivery mechanism for ACP math libraries. So we're trying to go towards predictive science, so we have regular releases for those. As a matter of fact, the next release will be in November, and we're adding at least 2 new libraries to that. So there will be 26 then, probably 26 at this point. We don't have time to add much more than this. But again, we're trying to really make sure we do all these things here to make sure this works well. OK, but of course, there are other packages out there. It's not just math libraries. We do have other packages that and so for that one, there is actually the Extreme Scale Scientific Software Stack, E4S, within the ECP, which you can get on e4s.ia. There's a website here, which kind of looks a little bit like that. And that's another community effort, which is actually headed by Samir Shende, which tries to get all the different packages together. So not just the math libraries, but visualization tools, programming models, like whatever, MPI, CUDA, I mean, all these things. Et cetera, et cetera, programming languages. And so they're all under the E4S package stack. And so this really tries to provide a container that these already pre-built, make it easier for people to link with them and use them. And the current E4S actually has more than 100 popular HPC software packages. It does provide this catalog. It supports different containers like Docker, Singular, Shifter, and Charlie Cloud runtimes, and so you can download these and use them for different machines out there. Actually, the current build cache has over 80,000 binaries, so it's huge. And it does provide them on different platforms here. And it does also give you some NVIDIA and ROCm and AMD options, which is, of course, not complete. That's just a subset of the whole E4S stack for GPUs. And then if you go to the E4S portal here, it has a doc portal, which provides you the location for each of the different products they have underneath. And so the whole idea is to make it easier for application to install these for their application. So here are just some more examples, which are kind of hard to see, I guess. But there's an example of the current build cache here for the you can see here, they do have also community policies. The community policies they developed, actually, they started with looking at the XSDK, so they were done afterwards. And the funny thing is, when we from the XST team looked back at the E4S ones, we thought we actually made some changes to ours in return. So we have been affecting each other. Down here, you can see the products. And so you see, right now, there are 101 ECP products. They do have quarterly releases, so the next one should be actually coming out this month. This was the one in May. And so they're also working on getting this all built with SPAC. I'm not sure if it's totally finished yet. And so they do have CUDA, ROCm, and some kind of machine learning parts here. They do have pipelines on Cori and NERSC. So what is, just a summary on E4S, so what is it and what is it not? So E4S is not a closed system that uses only DOE software. No, it actually uses software from anywhere and everywhere when it makes sense, right? It does require a certain quality, of course, for this. And there need to be open source. That's really important, which, of course, it's also not just a monolithic take it or leave it behemoth. They really try to work with people, you know. They try to make sure that people have what they need. So again, because it's all open source, it's not a commercial product for sure. It is really a vehicle for delivering high quality software products in collaboration with others. And then it's also not a simple package of existing software. So they're trying to really make sure that this all works well together. So they have a hierarchical software framework underneath. So there are different SDKs underneath. XSDK is one of them. So the whole XSDK package is a part of this. But there are other SDKs, like there's an SDK for visualization, for runtime systems, et cetera. So which they independently make sure that their portion works together as well. And so it does require some interoperability that this all works well, and they do expect a certain quality of the software to be part of E4S. Okay, so I did mention that there are other ways for you to learn more, to increase your software productivity if you want to learn more about getting better scientific software. So this is the Better Scientific Software site here over here. And you can see there are some reading recommendations. These are some of the libraries that are being discussed today. You can get more, and some of them newer things. Some of this was from last year. I only updated this year. The highlights were updated. But if you go to this website, you can get a lot of different things. You can go and search and find. And so there's also track 7 coming up in 2 days, where you can learn more about software productivity and sustainability. Okay. So we'll soon start looking into our lessons. And so again, there will be a lot of different types of hands-on lessons. So again, you have all these different options. You still have to think about which one you want to participate with, as you can't do them all. We've learned from the past, if we try to do too much in a short amount of time, nobody really benefits, so we try to loosen it up. But the disadvantage is you can't do all of them. Although I think they will all be recorded, and all the slides are available even through our website. So if you actually click on them, you can also see the slides. I hope everybody put them, and if not, they will do so soon. And so yes, you can get to our pages size here. You can get to the hands-on lessons later. Okay, so at this point, if you haven't really done your choosing of the different sessions, then I say you should go ahead and do this now. Remember, you have to go to that website and try to do this because we need to know, because very soon we're starting our first lesson here, and so we need to know which room you guys all want to go. Maybe this is not going to be an issue. Maybe it's just half-half anyways. But we just wanted to make sure that we don't have the situation everyone's in the breakout room and there's not enough room and they can't do it. So, okay. So please make your choices if you haven't done this yet. Again, here is the form that's available. You can click on it, or you can get to it through our tab on our intro tab. You can get there and start making your selections. So that way we can start looking into this, especially for the next session. It's important to see which ones of you want to do structured, who wants to do unstructured. And then what are our next steps here? So again, here, if you haven't done it, go ahead and do it. Then again, during breaks and lunch, we want you to submit the questions for the panelists. So again, that's optional. But if you have some questions regarding extreme scale scientific software, things like that, feel free to put it in there. You do have some time to do this still. And then I think this time here is wrong. I think the questions need to be submitted by 3:30. But the discussions with the numerical software developers, you have a little more time. So they just need to be submitted before dinner, okay? So I just realized that got slipped somehow. Again, so do that too, please. Okay? And then I do want to thank the ATPESC staff here for all their things, and I do thank you guys for being here and for continuing to make great contributions, discussions, etc. So I do want to leave some time here for questions now, so let me know if you have any questions. I know it's been a long day, so a long week. The day has been long yet, but the week has been long. So Since you had Sunday off, right? That's all, right? Yeah, that's not much, right? So, again, so who has not filled out their, oh, is there a question actually? Yeah, go ahead.
I was wondering if you could discuss more about SPAC, how it relates to this software.
SPAC, okay. I think you guys will get more about SPAC in one of the sessions, right? I guess Ray probably would know where. So the person actually...
So on the Software Sustainability Day on Thursday.
Yeah,
we'll
okay, so you'll learn more, but I can
we'll
still...
have a SPAC. I don't know what you guys are doing.
Yeah, I don't have that much here, and Todd Gamblin is actually the person who developed SPAC. You know, that's also the whole idea, that you are actually able to build the whole XSDK by just saying SPAC install XSDK. Of course, it's never quite that simple, but for a certain type of machine, it actually works. And Satish, who's here, makes always sure that this is the case. So where's Satish? So yeah, there. So yeah. So really, that was the overall idea, that you can just use a single command to do that. It's never that simple because of the dependencies. So when we actually start going to the more complicated machines, we end up accepting certain packages because it doesn't always work. You know, as you see in this complicated tree here, you do see all these different packages underneath, and you can already have problems right here. So sometimes what happens, we've finished building this, and SPAC actually changes daily, I should say, because people putting new packages in there, new connections to SPAC. What can happen that even after we have the XSDK finished, within a short time, if you use the newest SPAC release, it doesn't just build like that anymore, so we have to make more changes. And then keep in mind, all these different software packages are changing continually too. We are not on the same schedule. We can be, right? And so this is a very complex thing, but they keep working on it, trying to make it better. They're including more testing possibilities, so we can do SPAC testing and more of that, allow you to kind of run things more. Again, but it's a work in progress. You can see here, this is old. This is really from last year, and for some reason this time Todd did not send me the updated one. But I'm sure there are over 1,000 contributors at this point, and huge amount of packages because more and more people are using it. So sorry, that's all. But you get a lot more deeper into SPAC in 2 days. So yeah, but I'm not the expert on this. So are there any other questions? Yeah.
So I'm not a computer scientist, I'm a domain scientist. I'm just wondering, like there are so many packages in XSDK. Are all these very application specific, or can we just like once we write the code, or for example, doing some direct solvers? So is it interoperable between different packages?
There are some interoperabilities between the packages, right? So each one has to have at least one. And where it makes sense, you know. For example, you could run, well, if you solve a linear system and you want to use algebraic multigrid, usually you use it as a preconditioner for some Krylov solvers, which that might be in the same package, or you might have different sub-packages, you know. But then, for example, you might want to use a direct solver as a coarse grid solver, and you end earlier, and then you might want to use hyper to do that, and then use super U underneath. So that's one way, but you have to set that up. It doesn't automatically just do that. And so there are other connections. For example, a lot of these, like you can actually call to PETSC. You can use PETSC to solve for a linear system, and they might actually call hyper underneath or super LU, you know. So that we do have these connections. But a lot of them, for example, PETSC has a lot of different connections. MFEM has a lot of different connections. We start from the finite elements, you know. They connect to a lot of the different. I know Sundials also has a lot of connections to the different libraries. So yes, they are there. You will have to kind of set them up. In some cases, they're not always enabled in our XSDK build package. So generally, I do not actually recommend to use SPAC install XSDK because you usually only need a few. You don't need all 24 libraries, right? And so, but generally, you can install them and use a subset. So we're trying to really make sure that the subsets also work together. As a matter of fact, one of the things we've started to do for the XSDK is trying to test subsets and also on development versions. That's a new thing. So we can make sure that at least these interoperabilities don't break as the libraries keep updating, you know, but the whole XSDK will break. But at least if you maybe have those 4 important libraries that people use a lot together, we can test this. And it has helped us in the past that we very quickly found where somebody had made a change that wasn't really good, and we quickly could fix it because we saw it very quickly it broke, you know. So yeah. So we try to help. And one thing I should say, one of the community policies actually requires that each package has a clear contact point, so you can contact them if you have an issue with the package, and they're supposed to respond. You know? So yeah. And we try, actually. We really try to make our customers happy as far as we can.